Hey everyone, I'm excited to talk to you a little bit today about polymers. Polymers are all around us, from the cell phone cases that you have to cleaning supplies to um, the plastic binders that you have for your different classes to practically everything that our food comes in. Polymers are everywhere. Polymers have a wide variety of uses and properties, from cotton to fingernails, which would be natural polymers, to nylon and PVC. Polymers have transformed the world that we know. So if we were in class, I'd have you look at a couple different examples of polymers. One is water lock, also known as sodium polyacrylate. You've actually seen this before. It's polymer that's super absorbent, that's in baby diapers. We looked at it earlier in the semester. And then HDPE powder is high density polyethylene. We'll talk about that a little bit more. Water lock, or sodium polyacrylate that's in the baby diapers, is hydrophilic, having an affinity for water, or you might say that it loves water, it soaks it up, sometimes up to 500 times its own mass with distilled water. We'll try adding a little bit of salt to water lock and seeing what happens, and I think maybe we did that the first couple weeks of school when we were looking at different materials. High density polyethylene powder is hydrophobic. It's afraid of water. That would be something like moon sand, which I can have a demonstration put together for that. Grow frogs or grow dinos are also kind of fun little toys that are super absorbent, and they're made of the same sodium polyacrylate material that is in baby diapers. A little bit of background information on polymers. They are long, really, really long chain molecules, and they just repeat in a set pattern. The word origin for polymers, poly means many, so many repeating units. And mer is actually that subparticle that means unit. So many units, they just repeat in a pattern. There are some elements, not the entire periodic table by any means, but the few that I've listed here, and you'll notice that they are all nonmetals. They form covalent bonds and share their electrons in lots of different arrangements. But these are primarily the elements that we're going to use to make polymers. Where do polymers come from? They come from petroleum, which you might start thinking, wait a second, I thought petroleum was a fossil fuel, and I know that that eventually is going to run out. That is absolutely true, which makes me wonder, where are we going to be at with polymers and everything that comes in plastic in 15 years, in 50 years, when we don't have any more petroleum to mine out of the ground. So here's just a graphic that I found online that shows the different boiling points for the different types of fuels. So you've got fuel oil, and I think I can use fuel oil. You can break that down and boil that at 370. A little bit lower boiling point, 300 for diesel oil, kerosene, and gasoline. So when you get this petroleum or the crude oil up to 20 degrees, gas is what's going to come off first. Get it a little bit hotter, then you will have gasoline or octane, even hotter, kerosene, diesel oil, and then to get it before, I don't know if there's not another one down there, but 370 degrees, and that's when you could boil off the fuel oil. A little bit of a timeline on plastics. 1839 was when Charles Goodyear invented the process of vulcanization, which led later to rubber manufacturing. 1870, so quite a few years later, chemist John Hyatt further developed the making of celluloid, which is what they made film out of. Bakelite was one of the first synthetic plastics, synthetic meaning man-made. And you probably came across that in the TED Ed talk. Lots of different things that they can make, or that they did make Bakelite out of, including toys and the telephone that's shown here. 1926, PVC is invented by B.F. Goodrich scientists. A couple years later, we have polyethylene, which is what we make most of the things that are the plastics that are in your fridge or in your pantry. Polyethylene is super useful, and you can make it have a variety of properties, from being hard to being flexible. 1939, DuPont introduces the world to nylon. 1941, we have polyethylene terephthalate. That's the plastic that our Pepsi, Coke, Mountain Dew comes in, those pop bottles. 1939 to 1945, the development of plastics makes up to this point, makes them super high demand for production during World War II. In the 1950s, we have our first polyethylene bags. And we might talk about in this class how in many places around the world, and even in our country, I believe in the state of California and a couple other states, have banned the use of single-use plastic bags, like the kind that we'd get at Ed's or Walmart or Meijer, and they just require customers to bring their own reusable bags, mainly because it contributes a fair amount to waste in our landfill. 1954, we have polypropylene that comes onto the stage. Still in 1954, Dow Chemical invents polystyrene, expanded polystyrene. They've patented it. So even the the expanded polystyrene manufacturer in Ludington that makes lots of different craft foams, like craft wreaths and those green blocks of floral foam that you stick flowers into that can then suck up the water. They can't call it styrofoam because Dow Chemical has trademarked that. 1960s to the 1970s, plastics were further toughened and refined to allow them to compete with metals for different products that they would get made into. So this is a little bit of background information. Polymers can be created using addition and condensation reactions. So I'd like to share a little bit more about that. For addition polymerization reactions, if we were in class, I would have you find a partner, and you would represent a carbon atom, and your partner would represent a carbon atom, and you would hold your hands out and form this double bond that's between you and your partner. Excuse me. Then what happens as we're standing around the room, you would break that double bond. Well, really just one of the bonds, still holding one of their hands. Then you'd reach out with your other hand and grab a neighboring partner, so that we've got one super long chain of everybody holding hands that really is just single bonds. But it started with this would be ethene molecule, which is a type of hydrocarbon, or a type of fuel. You can kind of see, I've highlighted in here, here are 5 of the 7 different types of plastics. You'll notice that 2 and 4 end with the same 2 letters, and plastic code 2, recycle code 2 is high density polyethylene, and 4 is low density polyethylene. But what I want to draw your attention to is how you've got the carbon single bonds that are between, that's like the backbone of all of these different polymers. And you notice that the dots are on the sides, both in the front and the back. That's because these chains would continue. They're so super long. You've got this benzene molecule down here in the styrene. It says styrene monomer. A monomer, mono meaning one, is just one little section of the polymer. and it's got like this hexagon shape. What that really is a benzene ring. And essentially you've got a carbon at each one of these corners, which makes polystyrene, that's what the PS stands for, that styrofoam essentially. It makes it really hard to recycle and break down polystyrene because of this extra 6-ring carbon molecule here. PVC, polyvinyl chloride, is number 3 up here. And you can kind of see where the hydrogens, every other hydrogen has been taken off and replaced with a chlorine molecule. With the name polyvinyl chloride, that's where the C comes from. It's from chlorine. 5 is polypropylene, and you can kind of see where the name or the abbreviation comes from in its name. We're also missing plastic number 1 and plastic number 7. 7 is actually just labeled as other, and that could be any other plastic. This is kind of a comparison. Let me move my picture here. This is kind of a comparison of high density polyethylene and low density polyethylene. The HD stands for high density and the LD stands for low density. And I always thought this was a little confusing. If you're talking about high density polyethylene, that's actually a structure without branches. So it would look like this picture that's down here with the C's and the H's connected. Then you've got low density polyethylene, and that would actually have branches coming off of it. And I've always thought, why would that be low density? That seems like that should, if you've got branches coming off, that seems like it would be high density. But what ends up happening is when you've got the branches that come off that main chain, that allows the molecule to spread out and take up more space. So if it takes up more volume, that's why it's actually low density when it does have the branches coming off of it. And it's just carbon and hydrogen in the molecule, in both of them, high density and low density. Oops. And here's just a little bit better picture. So you've got the branches that are coming off. Each of these little circles would be your carbon. And you can kind of see where it's spread out, and that's why it ends up being the low density polyethylene versus without a whole lot of branches, it can be tighter, compact together, and that's where you get your high density polyethylene. And I'll let you just take a second right now and look at this slide because there's a lot of information here. And if you had these different plastic pellets, and in the sinkers and floaters lab, you'll use some of these materials to figure out the identity. So if you just had water, for example, and you put all 6 pellets in here, looking at water, plastic number 1, known as peat, see if I can find my mouse here, would not float on water, whereas plastic 2, yes, it would float on water. Plastic number 3, where it's just listed as a V, that's PVC, polyvinyl chloride, that would not float on water, it would sink to the bottom. So that's kind of how you read this, this chart or this table. A condensation, I said that there were 2 types of making a polymer. We had addition polymerization, and this is condensation polymerization. The only thing that I want to add with this is that you do have a smaller molecule that ends up being formed as a byproduct. This is also known as a step reaction. This is how peat, and I'm drawing a blank, that's I want to say it's polyethyl terephthalate, really long name. That's what peat stands for. This condensation polymerization reaction is how you would get like our pop bottles or our Dasani water bottles. Holding the chains together, we have covalent bonds, which are quite strong. For an example, rubber. If we get to be back in class, we're going to make slime. And those are weaker bonds held together by intermolecular forces. And then you also have something known as entanglement, which is what happens in the high density polyethylene. Since everything is so compact together, even though you don't have a whole lot of branches, imagine this. Imagine I had 50 pieces of yarn that were each 6 feet long, and I put them all together and threw them on the floor. What would happen if I tried to pull out just one piece, knowing that they're all 6 feet long? So that's what entanglement is. And that's kind of what's happening inside high density polyethylene, which would be like the plastic that's in milk jugs. So PVA slime, probably one of my favorite labs, and it always just blows me away that the laundry bag, if I move my picture, I think you can see it a little bit better. The laundry bag that's actually a hospital bag here, in the hospital, they will take soiled linens like bed sheets and hospital gowns, and they put them in laundry bags like that, and they put the whole bag right in the washing machine because it's made from a water-soluble plastic known as PVA or polyvinyl alcohol. The same type of plastic is actually in Cascade dishwasher packets or Tide pod packets, which is why when you throw these in your washing machine, the plastic that's on the outside holding the detergent in just dissolves. But I have polyvinyl alcohol, and it comes as a powder, or we could take one of these laundry bags and cut it up and make our own polyvinyl alcohol solution. Mixing that with a little bit of borax, which is laundry soap, mixing those two solutions together, and we can make some slime, which is pretty cool. So I just wanted to point out with the polyvinyl alcohol, that's the molecule that's on the top and on the bottom. And what's in the middle is that I've circled in green. That's actually a borax molecule. And you'll notice that the bonds aren't solid lines here because they're so weakly held together. That's what gives slime slimy properties that it has, is because those bonds are so weak. The borax is in the middle, and then you've got the polymer chains. The polyvinyl alcohol is already a polymer. You're just going to link those molecules together a little bit differently using the borax solution. So there are two different types of heat treatments, or the plastics can be either thermoplastics or thermosets. And I always thought that this was pretty straightforward because a thermoset plastic is set. You can't like recycle it very easily. And we're going to make shrinky dinks in class or even in your oven at home. And once that plastic gets heated and set, there's not an easy way to recycle it. Whereas if you have a thermoplastic, it's soft, sometimes it's stretchy, it's easy to recycle. And so you could heat it up and reform it into something else fairly easily. And then the last one we're not going to spend a ton of time talking about is an elastomer. And that would be something like rubber. I think this is our last section that I want to talk about, polymer processing. So you've got all these plastic pellets, like in the sinkers and floaters lab. You've got all these little teeny plastic pellets. What do you do with them? How do you use them? How do you make stuff out of them? The first two ways are an extrusion. The second way is an injection mold. So you can tell that the plastic pellets or powder go in the top in both situations. And then if it's an extrusion, it will come out, and it might, if it was something like styrofoam, as it comes out over here on the left-hand side, it might expand as it comes out. It depends on if it's just like plastic cord or if it's like a styrofoam type of material. Injection moldings mean that you have the mold here on the end, so it's not just being extruded and coming straight out. it would actually fill up the mold. So you'd have to calculate exactly how much of the plastic you need so that you don't overfill the mold. And both machines have to have heat applied. And then, of course, you can kind of see that corkscrew thing in the center. That's turning and spinning the plastic as it's being heated. So you have a thorough heating as it gets pushed to the left in this case. And then the last two, film or blow molding, and then compressor or transfer molding. And both of these pictures, I think, are pretty self-explanatory. You guys have all seen the soda bottle preforms, and they start like this on the left. And as hot air gets forced into them, plus you're heating up the preform itself, it fills the entire, it fills the entire mold. And so I think you probably have noticed before that a 2-liter bottle has thinner plastic than like a 20-ounce bottle. And that's because they both start same size soda bottle preform, but you just need to expand the 2-liter bottle more than you would a 20-ounce bottle. The compression or transfer molding, that's when you would have a softened material, or in this case, the picture's calling it a charge. Once that is warmed up a little bit to make it softer, then you press it between a top and a bottom plate to give whatever material or object you're trying to make. All right, so just as a quick review, in this video, we covered some polymer basics, history, types of polymers, reactions with heat, and how you could process them. The different things that you should have learned are that polymers are long chains of repeating units called monomers. Polymers can be natural or man-made. Synthetic polymers, man-made polymers, come from petroleum. Polymers can be made with addition or condensation reactions. Polyethylene comes in high density or low density polyethylene, and the arrangement of the chains determine the polymer's properties. The number on the bottom of a plastic container tells you the identity of the plastic. A solution of PVA, polyvinyl alcohol, can be mixed with borax to form links between the chains, and slime is created. Thermoplastics can easily be recycled, whereas thermosets are set in their shape once they're heated. And plastics can be produced and processed in a variety of ways that we just talked about, including extrusion, injection molding, and compression molding. I hope you found this helpful. Thanks, everyone.